Okay, here's our final section for chapter 4b. We're going to be doing inverse trig functions. So take a little trip back to integrated 3. Last year, we talked about inverses as an essential skill. The main one, well, we did inverse of a ton of different things, but we did end up having to restrict the domain on one of the graphs specifically to make sure that the inverse itself was a function. So here's our little trip down memory lane. It was the parabola. So if we took the parabola and then we went through and we reflected it over the line y equals x, then we would have gotten the blue graph as the inverse. Problem is, the blue graph does not pass the vertical line test because it is not a function. We want the inverse to be a function. Another way we could see that the inverse was definitely not going to be a function, if you look at the original and you tested the horizontal line test, it fails. So I knew there were going to be problems with this from the jump. So what we want to do is we want to restrict the domain on the original function so that when I reflect it over y equals x, I have another function. So we went through last year and instead of doing plus or minus the square root, so a non-function parabola, we just kept either the top part or the bottom part. It didn't matter which one. Then we went back and you reflected it back to get it to line up with the parabola. Problem is, too much parabola. So we had to cut off half of the parabola. And now, by restricting the domain of the parabola, so at the vertex, which is where we cut it off, if we reflected over y equals x, then we could guarantee that the blue graph was also a function. This is what we are going to be doing. We're going to be doing this with our trig functions as well. So that was our quick aside from last year. And let's take a look back over here at the sine curve. So if I were to take a look at the sine curve and I want to think about the inverse, I would do the horizontal line test on this guy. Well, it's going to fail. So many places, an infinite number of locations actually. So I want to try to get a portion of the sine curve that I know is going to pass the horizontal line test. And ideally, I really want to stay close to the origin. Like 0, 0 is a good place to be. So if I take a look, I've got this little red box area. So if I look within just the red box and I test the horizontal line test, it's going to pass every single time, which means that the inverse, if I restrict the domain to this location, the inverse of the sine graph is also going to be a function. So that's my plan. Let me get rid of all of those green lines. Okay, well, where is that? Well, we're going to restrict it. So if you take a look at the right-hand side over here, we're going to restrict it to a domain of negative pi over 2 to positive pi over 2. And then the range that keeps us from the negative 1 to 1 also. So instead of the entire sine curve, we're just going to take a look at that little tiny chunk, negative pi over 2 to pi over 2. Then, if we take those points, so remember, inverse is the exchange of x and y. Exchange of x and y, that hasn't changed, still the same definition. So if I took my points from my regular sine curve, I'm just going to take my x values and make them y's. So these guys are going to go over there, and then my y values are going to go over there. So they're just going to swap. If I do that, now I have this arc sine graph. You'll notice that it passes the vertical line test the whole time. So this is my inverse of sine, which can be written a couple of different ways. You can call it sine inverse, so with a little negative 1 exponent like we've had in the past, or you can call it arc sine. They're technically the exact same thing. So we have this restriction now for arc sine. Okay, we can do the exact same thing with cosine. Should have known, as expected, that if I drew my horizontal lines, this thing was going to fail a ton of places, like so many places. So what I want to do is I want to focus in on a specific section of the cosine graph so that if I'm within that limited domain, I'm going to pass the horizontal line test the whole time, which I am. In this case, it's not right around the origin. If it was, then I would be failing the horizontal line test. So just kind of shifted it over a little bit. So if we take a look, now we've got our domain of 0 to pi for arc cosine, and then our range is still negative 1 to 1. We want to make sure that we're still getting all of the y values. I don't want to chop part of those off. So now I'm going to do the exact same thing. I'm just going to take my x and my y values, and I'm going to exchange them, since that's what inverse means. So I'm going to exchange my x and y's. I'm going to plot those points, and notice now it passes the vertical line test everywhere. So that's good. Next one, tangent. Tangent, we can hover right around the origin, which is really nice. But if I go past a vertical asymptote, so if I go past one of them, I'm going to start failing the horizontal line test. So right there, we know that there's a vertical asymptote there and a vertical asymptote there. We know that once you go past those, you're going to start duplicating the tangent curve. So we want to stay right within the single regular period. Now, the domain and the domain's a little bit different this time. Notice there's no brackets on the domain. Well, that's because the graph doesn't exist at negative pi over 2 and pi over 2. Those are undefined. And then we still have all the y values that we would normally want, which is the range. So I don't want to cut those off. And then we're going to go ahead and we're just going to exchange the x and y's to be able to get our arctan graph. Then I can go through and see, look, I passed the vertical line test everywhere. So now my inverse is a function. So without actually having graphed sine, cosine, tangent, cosecant, secant, cotangent, we wouldn't know what the restriction was supposed to be for the inverse, but we had to restrict it because we want the inverse to be a function. Okay, so how does this relate back to the unit circle? Well, we can go through and identify the radians on the unit circle and then just see like, okay, arc sine and arc tan were both from negative pi over 2 to positive pi over 2. That's where they were on the graph. That was the section that we kept. So we only want to go down to negative pi over 2 maximum, don't go past it, and up to pi over 2. This is like a no-go zone. We don't want to go there. That's bad because arc sine and arc tan don't exist in those locations because remember we restricted the domain to guarantee that it's a function. Same thing over here with arc cos. With arc cos, we were from 0 to pi only. We don't want to go past it, and we don't want to go below. So if we take a look back at our sketches on XY coordinate and compare it to the unit circle, these are the restrictions that we have. You'll notice that arc sine and arc tan have the same restrictions. That's kind of nice. And then arc cos has its own restriction from 0 to pi. And then there's our domain restrictions. Only difference between arc sine and arc tan is at the negative pi over 2's. So arc sine and arc tan arc sine at negative pi over 2 and positive pi over 2 actually exists. Like you can do a value of that. Whereas arc tan, not so much because you had your asymptotes at that location. Okay, so let's see if we can actually do this. So here's what I would normally do. I take a look and I pay attention to like which arc this is. Now, if this is arc sine, arc cos, arc tan, arc sec, arc cosec, arc cotan, then you are looking for an angle. Your answer is going to be an angle. So if I've got an arc of something, you're looking for an angle. So I'm trying to figure out where sine is a half. Okay, well, I have to think about my restriction. It's got an arc in it. Arc sine, it's a no-go on the left-hand side, so it can't be over there. Where sine is a half, well, half's positive, sine is up, so I want to go up half. So that would be that guy right there. My question is what is that theta? Well, I know that theta, that is pi over 6. You have to make sure that the radian that you give is bound literally on the x or y axis, however you want to look at it, between negative pi over 2 and pi over 2. So I know that this answer is going to be pi over 6. I was looking for a theta. I got a theta. Okay, let's take a look at the next one. And that's it. That's the answer. There's only one of them. Because we restricted the domain, you're not going to have an infinite number of answers because that wouldn't be a function. This one is a function, only one value. Okay, I have arc cos. Arc means I'm looking for a theta. So basically what this says is that cosine of something, cosine of some angle, is equal to negative 2. Hold on a second. Cosine is the relationship between the adjacent and the hypotenuse. So I know cosine of whatever my theta is adjacent over hypotenuse. This says that I would have an adjacent side of 2 and a hypotenuse of 1. That's a no-go. This isn't even possible. Remember that the hypotenuse in a triangle is always the longest side. It's not possible for the adjacent side to be longer. Okay, let's take a look at the next one. Arc sine. Okay, this is an arc, which means I'm looking for an angle. All right, arc sine. Okay, sine's negative. Okay, arc. Take out my restriction, can't go there. I want sine to be negative, so I'm going down, and that's actually pretty steep. So I think that's my triangle, where this is negative root 3 over 2. Now be careful. Arc sine is up to positive 2 or down, up to positive pi over 2 or down to negative pi over 2. You have to make sure that the theta that you give is actually between those two things. So I know that this would be a pi over 3, and this theta specifically is negative pi over 3. And yes, negative pi over 3 is in between negative pi over 2 and positive pi over 2. Okay, let's take a look at the next one. Okay, so different notation, but asking the exact same question. If you see cosine inverse, this is the same thing as saying arc cos of negative 1. It's an arc, which means you're looking for an angle. Okay, arc cos, okay, that means I can't be down here. I can be between 0 and pi. That's it. Where is cosine negative 1? Well, cosine negative 1 is over here. That is at pi exactly. So theta is going to be pi. Notice it's just a whole bunch of little pictures and figuring out, like, how well do you know your 6 trig? Arc cosec. Okay, so it's an arc. We're looking for an angle. Now, the reciprocals in the originals have the exact same restrictions. So cosecant goes with sine. Arc sine has a restriction of negative pi over 2 to positive pi over 2. Okay, if I see arc cosec, then I know that this is arc sine of, well, the reciprocal of that is root 3 over 2. Those are going to come from the exact same angle. Okay, so I want sine to be positive. It's pretty steep. That's this guy. I think we're at pi over 3. Okay, next one. Arc tan. Arc, that's an arc. We're looking for an angle. Okay. Restriction of arc tan. Can't be on the left. Negative pi over 2 to positive pi over 2. That's it. Then where's tangent negative 1? Oh, these ones are my favorite because these are pi over 4s. Now, be careful. You have to be between negative pi over 2 and positive pi over 2, which means this is going to have to be negative pi over 4 as your answer. So theta is negative pi over 4. Now, in addition to being able to evaluate arc of length, whatever it is, trying to find an angle, we can also do compositions of them. So this kind of goes back to what we did in integrated 3, where you had to do f of g of x. Now, the thing is, you got to start from the inside and work your way out. So let's say we wanted to find arc sine of cosine of pi over 6. The first thing you're going to do is the thing inside, cosine of pi over 6. So start with the inside and then evaluate. Okay, well, we know that cosine pi over 6 is root 3 over 2. So now replace the cosine of pi over 6 with root 3 over 2. You just found out what it is. Now you're trying to do the arc sine of that. Now, arc sine means you're looking for an angle. And now, because you're dealing with the arc, you have to make sure that you obey the domain restriction. So start on the inside, work your way out. Same thing applies. If the very first function you run into as you're looking at this, like I see that the very first thing is arc sine. That's the very first thing. That means that my final answer is an angle. Whatever it is. Now, if they were reversed, if it was cosine on the outside, then my final answer is the cosine ratio, whatever it is. So, inside, work your way out. A couple helpful tips for you. Okay, let's take a look at some examples. Okay, so let's start on the inside. So the inside says that we've got arc cos of negative half. So let's just do that. I don't even see what's on the outside because it doesn't matter. Arc cos. Okay, can't be down here. Whereas cosine negative half, that's left. And it's steep because we want the adjacent side to be pretty small. From 0 to pi, this is going to be at 2 pi over 3. So this theta is equal to 2 pi over 3. Now I'm going to replace that for all of the yellow stuff in here. So this is yellow, replace the yellow. So now I have sine of 2 pi over 3. Well, sine of 2 pi over 3 is going to be root 3 over 2. My final answer, different color, is going to be root 3 over 2. So you've finished. You've reached the outside of the trig that you're looking for. Okay, let's do the next one. Start with the inside. Arc sine of 3. Okay. So this is saying arc sine of 3 is equal to theta. This says that sine of theta is equal to 3. So sine of something is equal to 3. Okay, we have the exact same issue again. This, as we did before, remember, sine is opposite over hypotenuse. What this is saying is that you have an opposite side that's larger than the hypotenuse. This doesn't make any sense. This is not possible. And yeah, there are going to be a handful of those. You got to pay attention to this. Okay, let's take a look at the next one. Okay, we're doing arcsec. All right, arcsec. So if I have arcsec of 7 is equal to, I'm looking for an angle, this means that arc cos of 1/7 is equal to theta. Okay, so we know we can go back and forth between these. So this is basically cosine of the angle I'm looking for is 1/7. That's possible. The adjacent side here is definitely smaller than the hypotenuse. Okay, but it started out as an arc, which means we have to obey the restriction for arc cos. Arc cos and arcsec have the exact same restriction. Okay, cosine is going to be 1/7. That's not special. That's okay. I just want to make sure that my cosine is going to be positive. So adjacent over hypotenuse, do a little bit of Pythagorean theorem. This is going to be 7 squared minus 1 squared, so that's going to be 48. Okay. Now sometimes the best you can do is just create the triangle, like the theta, that actually has this information in it. So cosine of 1/7, yep, it's right here. It's in that triangle. I made it happen. Now, use that triangle to do tangent of the angle you just created. Okay, well, the angle I just created is inside the yellow triangle. So go to the yellow triangle and identify tangent. Tangent's going to be opposite over adjacent. So it looks like tangent of theta, theta being the little yellow guy that we just created, is going to be root 48 over 7. I've reached the outside. That's my answer. No, opposite over adjacent. Oh, happy I caught that. That would be over 1, which I don't have to put, but I can if I want to. Okay, fixed it. Thank goodness. Whew. All right, let's move on. Sine of 5 pi over 3. Okay, so I'm starting on the inside this time again. Sine of 5 pi over 3. There's no arc in that, so I don't have that restriction. 5 pi over 3 is fine. So I'm going to take out my my unit circle. I'm going to find where 5 pi over 3 is, which I know is down there. And I know sine of 5 pi over 3 is equal to negative root 3 over 2. So there's my answer to the yellow thing. Okay, so now I have arc cos of the yellow value that I just got, negative root 3 over 2. Okay, now this is an arc, so you have to restrict this. So nothing down here. Up there, where is cosine going to be negative? Remember, we're looking for a theta here. Where is cosine going to be negative root 3 over 2? Well, that's this guy over here. It's not a pi over 3 anymore. It's a pi over 6, and you have to make sure that it stays from 0 to pi. I think theta in this case is going to be 5 pi over 6. Okay, moving right along. Now, take a look at this next one. We've got tangent. And if at any point in time you want to try these on your own, I highly recommend. Just pause, come back, check your answers. Okay, not an arc. I don't have to restrict it yet. Tangent of 3 pi over 4. Well, I know where 3 pi over 4 is. It's right there. I know tangent of 3 pi over 4 is going to be one of the ones, which I really, really like. This theta is going to be equal to, oh, nope, I already know theta. This is going to be negative root 2 over 2, root 2 over 2, 1. I know that tangent of 3 pi over 4 is going to be equal to negative 1. Oh, forgot my negative sign. Put my negative on there. So I know that my yellow is actually going to be negative 1. Okay, now I've got arc cos of negative 1. I want this to be equal to a theta. Okay, there's the negative 1. Now I've got the restriction. Let's cross this out. Cosine's negative 1. Well, cosine's negative 1 over here. It looks like theta is going to be at pi. Okay, and then you start chipping your way through. So start on the inside, work your way out, and see if you can answer the next couple of questions. And it's actually okay if something's not on the unit circle, like this arc cos 2/3, that's not on the unit circle, which is okay because we can just draw a triangle. This does have the restriction though, so not down here. Cosine is positive, so I want to be over here. I know that it's going to be adjacent over hypotenuse. It's going to be 9 minus 4 square rooted, that's root 5. Okay, this is the triangle now that you're going to use. Then we want to do tangent, and let's go ahead and call it theta. We want to do tangent of theta. I'll just use the yellow triangle that you made. So tangent of theta is going to be opposite over adjacent. So our answer here is going to be root 5 over 2. Okay, I want you to pause the video. If you haven't already done so and tried to do some of these yourself, I want you to pause the video, see if you can do question number 13 and question number 14, then come back and check. Okay, so on question number 13, we do need to obey the restriction because it does start with an arc, which puts us in the 4th quadrant. It's not special. It is Pythagorean triple, though. Go ahead and fill in the side lengths and then just use the triangle that you made to do cosine of everything that's in there, which is going to give us 4/5. Okay, see if you can do the next one. Pause it and then come back. Okay, I took my arc cosec of negative 2. I'm looking for an angle. Went ahead and just turned it into arc sine of the reciprocal, negative 1/2. Go ahead and put it in the unit circle. Make sure that you obey the restriction because it is an arc. That's going to put me at negative pi over 6. Then I'm going to do secant of negative pi over 6, and I will get 2 root 3 over 3. Okay, question number 15, home stretch. I think those are our last 3 questions. So it's the same idea, except now we've got variables flying around in it. You still need to make sure that you obey the restriction. Don't assume that the ratio is negative. Assume that the ratio is positive unless you are told otherwise. So if you take a look at question number 15, I am going to assume that this arc cos of 3x, now I don't know what x is. This could be a super tiny number, super large number. I have no reason to believe that the arc cos of 3x doesn't exist, though. So if it was just 3, then yes, of course, I have major issues with that, but I don't know what x is. So I'm going to go ahead and take my arc cos of 3x. I'm going to set it equal to theta, because if it's an arc, I'm looking for an angle. Basically, this says cosine is going to be 3x over 1. Now, I don't know what x is, so I can't say, no, this ratio is too big, it doesn't exist. depending on what the x value is, this cosine is actually going to exist. So let's draw a picture. Now I have no reason to believe that that cosine is negative. So obey my restriction because it was an arc to start with. And I'm just going to go ahead and put this in the first quadrant. Again, I'm not being told x is negative, and I'm not going to assume it is. Draw a theta that actually represents this, and then put the values where they go. So adjacent, 3x over hypotenuse 1. Do the Pythagorean theorem. We're going to get 1 minus 9x squared for the missing side. Now, you just created cosine of theta is equal to 3x. It's right here. It's in the picture. You're going to do the exact same thing you just did. Now, we're going to work our way out. We're trying to do sine of theta. Well, we have a picture for theta. We should be able to find sine of it. So sine is going to be opposite over hypotenuse. So this is going to be 1 minus, or the square root of 1 minus 9x squared. That's our answer. The best we can do, because we have an unknown value in there. Again, don't assume that the x is negative unless you're told so. So take a look at question number 16. You're being told that the ratio is negative. Okay, so with that being said, starting on the inside, arctan. Basically, this says tangent of some angle is going to be negative x over root 5. The ratio is negative. It is an arc, so restrict like you normally would. Out of these two quadrants, tangent's negative down here. So there's my theta, and then it's going to be opposite over adjacent. Do the Pythagorean theorem. So that would be leg squared plus leg squared square rooted. Okay, so we just made tangent of theta true. Now we have a representation for theta. It's in this triangle. Now I can do secant of that theta. So use the theta, this picture that we just created. Secant is 1 over cosine. Cosine is adjacent over hypotenuse. So this is going to be hypotenuse over adjacent. And it's totally fine to leave it like that. Not a problem at all. Okay, last one, arc cos. Now I have no reason to believe that those are negative, so I'm just going to assume that they're positive. Basically, this says that cosine ratio is m plus h all over 3k. It did start as an arc, though, so restrict it. Can't be there. Don't assume any of the variables are negative unless you're told the ratio is negative. So I'm going to put it where cosine's positive. This is the theta I'm creating. It's adjacent hypotenuse. Do the Pythagorean theorem. It's going to be hypotenuse squared minus leg squared, square rooted. Don't even mess with the math. Okay, we just made cosine of theta exist. And there's theta. Now, we want to do tangent of that theta. Well, tangent of that theta is going to be opposite over adjacent. And just leave it. Don't do anything else with it.